So who the heck am I? I've been talking to you all quarter. I haven't been saying a ton about me. So I'm a Berkeley and MIT grad, and I've roamed through 2 careers before I got here, chemical engineering and EECS with a MEMS specialization, so microelectromechanical systems. I've done big company R&D at Chevron Research, and then at HP Labs, and then after the split into Agilent Labs. And for the last dozen years, I've been in the more entrepreneurial space you can see here. Ice911 Research, you'll hear a lot about today. That's my environmental nonprofit. Stanford, here I am. You see what I do here. I'm associated with Roger Howe's MEMS and NEMS group over in EECS formally, and attend some of his group meetings and help sometimes mentoring his and Beth Pruitt's students. But I'd say the most time I spend here at Stanford is this class these days. This is the 4th time I'm teaching it. And then my day job, what actually is where I earn my living, is my engineering consulting firm, Small Tech Consulting. The successor really to my solo practice that I've still kept alive, MEMS Insight. And over this last dozen years, I and my colleagues, we've consulted for over 40 companies. We do a lot of stuff, design, invention, prototyping, strategy, IP, it's due diligence. It's actually a blast. I have a really great team. And over the years, I've gotten a lot of patents issued in various things, and I've got a bunch of patents pending. So I love to invent, and I'm one of the entrepreneurs we'll be talking about here. But I wanted to emphasize before going any further, you know, people get up front and they talk about I and me, and it's always about the team. Who's helping you? You can't possibly do most of what most of us try to do on your own. And so who's your team? And I'm lucky enough to have, just on the technical part, we've got another couple folks helping on the management side, giving me management advice, because you might have seen in that academic credentials, I don't have any formal management training. It's all been on the job. But I've got this team of, I think, 16 here, and we're about to add one more, almost entirely PhDs. And the one who's not a PhD is one of my key business advisors. Wow, she's absolutely phenomenal. And we are a really compatible crew, and we just love working together. And I'm just blessed. So it's all about the team. We're going to jump through a few more things through this class. We're going to do a quick review on what's the climate situation. You saw a bunch of this at the beginning of the quarter with John Coomey and Terry Root speaking. And then we're going to go into what the latest IPCC assessment is looking like, because they're starting to release results. And then we'll talk about why you would consider geoengineering. We've talked about many more straightforward engineering approaches. We're going to get into geoengineering. We're going to get into my project, which is not quite geoengineering. And then we'll do a little bit of a class wrap-up. So this was one of John Coomey's charts that he showed us. And just as a takeaway summary from this, global CO2 concentration is higher than at any time in the past 800,000 years. I think in his book he only had gone back 400,000, so now he's doubled that history. And that's a big deal. Why is that a big deal? We'll talk about that right here. People have linked that pretty unambiguously to the temperature rise that we're seeing. And in all of the models that people had, every time they look at it, we find that we're exceeding the most pessimistic estimates that people had made. This one is courtesy of Ken Caldera, and in fact, several of the geoengineering slides in this background are. He really takes a serious look at geoengineering over time. And the bad news is there's no practical way, in his view, to see emissions reduction to be able to reduce temperatures this century. So what do we do? And in fact, a lot of the people looking into geoengineering, I saw beautifully reasonable questions from you all on why would you do this? Or this is the only hope. You know, what Ken's point is, and what my point when I started my project is that you want to have it studied so that if your backs are to the wall someday, It's the option you really don't want to have to use, but if your backs are to the wall, you'll understand what the risks and the benefits are. So you're doing your homework in advance to know, are we going to go there or not? So the CO2 emissions keep exceeding all these scenarios that were estimated. And what's going on? Why does that raise temperature? It's changing the equilibrium set point in the atmosphere. You know, as you're absorbing radiation and you're re-radiating out to space, as you change the chemical composition of the atmosphere, you've changed the set point, where that's going to equilibrate to after a while. As we keep increasing CO2 or methane, you know, other greenhouse gases, that set point with this given amount of incoming radiation keeps rising, and we haven't equilibrated yet. And so what people are saying, again from Ken Caldera, 2008 paper with Matthews, preventing further warming would require near zero emissions right now. But we don't seem to be doing that. The IPCC fifth assessment report, they've just started publishing parts of this in October. The full thing will be published coming in 2014. But they've published the physical science basis. And I really enjoyed, I don't know if you call any of this enjoying in its way, but I found really informative going through the summary for policymakers, easily available online. You can see it here, ipccdata.org. And you can see the assessment of, you know, what's been happening with CO2, what the summer sea ice extent has been, what the average upper ocean heat content is, what the global average sea level change is. This is really careful work. If you read these reports, these are hundreds and thousands of scientists, depending which working group you have, going through, it appears to be semi-infinite peer review, to go through making sure that they are presenting what is the most unbiased data possible. If anything, the IPCC has often been faulted for being a bit too conservative because they want to be sure not to let out conclusions that strike anybody as alarmist. What I found most alarming, because we're kind of familiar with what's been happening, was their projections for the future, depending on various scenarios, basically running around what kind of CO2 is going to be, what sort of CO2 level are we looking at for the rest of this century. And the global mean sea level rise becomes really quite large. I mean, it's already large enough to be causing problems to coastal cities, right? We all know that. This is in meters, and this is by 2100, and it's really becoming quite large in the worst case scenarios. And remember, a couple slides ago, we said we always seem to be exceeding what the worst case scenarios are saying. So we really have a problem here. MIT years ago put out this greenhouse gamble when I started my work. So I started worrying about this climate situation a lot back in 2006 after seeing the Al Gore Inconvenient Truth movie. And at that point, the greenhouse gamble was this wheel of fortune. If you clicked on it, your chances were really good. You know, more than 50% of ending up at 2.5 degrees sea temperature rise or less, which is alarming enough. And this was live online. It may still be. The last time I dared to check in, which was a couple years back, all of this has collapsed into this teeny wedge here. That is, according to the more recent estimates that MIT policy and climate folks had made, there is a snowball's chance of us getting away with less than 3 degrees sea temperature rise. And the chances are really much, much worse. Are that we'll get to temperature rises that are much, much worse. Again, why do we care? I'm pretty sure I've shown you this chart before. This was Terry Root taking with a graphic artist the conclusions from the IPCC fourth assessment report and saying, well, so if we rise a degree C, you know, fine, I get more days at the beach, right? Why is it a problem? Well, you have a number of really horrific consequences from temperature rise continuing. And the ones that got my attention were this extinction of most of, or many of the known species, you know, up to close to half of the known species, because, you know, mass extinctions, well, I'm not sure that's going to be good for humans either. And so what we have as a conclusion here in the IPCC's latest assessment report, this 5th assessment report, I'll read this aloud. Cumulative emissions of CO2 largely determine global mean surface warming by the late 21st century and beyond. Most aspects of climate change will persist for many centuries, even if emissions of CO2 are stopped. And as we've already got enough inventory in the atmosphere, we're still equilibrating to this new set point. This represents a substantial multi-century climate change commitment created by past, present, and future emissions of CO2. You can see why I was so fascinated by Professor Brent Constant's lecture of a way to sequester CO2 in a way that looks workable and even profitable, which means that it could go to scale. This is scary stuff. And, you know, I can't bring myself to give you this scary stuff without having a ray of hope too, but it's pretty scary. So, what's the bright side? Well, it's opportunity. There are a lot of things one can try to do. And personally, I find it's a lot easier to live with this by going all out to do what I can. And I find that a very helpful way just for my own peace of mind. So, what are our choices? Mitigation, adaptation, and suffering. The climate problem's big, urgent, and misunderstood, which makes it great for starting something new. And Stanford, one of the more entrepreneurial universities around. And of course, John's view is that you have lots of entrepreneurs working on lots of things, trying things, seeing what works, seeing what fails, and then, you know, iterating to good solutions. Business needs environmentalists, and environmentalists need business. So the reason I couldn't come to the class where Dave Duff was speaking is because I was at the Cleantech Open, which talk about a hotbed of meeting other entrepreneurs who are attempting to do something in the climate space. This was a very amazing experience. And because Ice911 got to be a semi-finalist, which in itself is amazing, we're the one nonprofit who's ever been accepted to do that, we got to go through 6 months of very intense mentoring. And here were the grand winners, Powwow Energy. And, you know, there were just a lot of people participating in this. They made sure everybody who participated won in new connections and new mentoring. Rex Northern, he's spoken in this class before, actually, in past quarters. You could probably see it online on YouTube if you wanted to. And the winner, and I believe that's Eric Stieb, and who helped run things on the Western region. Really neat, really neat. And the proud CEO of Powwow Energy. And the grand prize winner came from 5 category finalists. And I wanted to just show you the diversity of things that people are working on. Air, water, waste, polymer green. Oh, these were nice people. They are off and running already to deal with landfill waste plastic in a really nice way here and in China. Energy generation, Helion Energy. Talk about diversity. These folks are working on fusion energy in a safe way. Green Building, Bioadhesive Alliance, starting from, yes, the most humble thing you can think of, swine manure. But they're doing something really useful. HJ3 Composite Technologies, these guys are using, I believe these are the ones who are using carbon nanotubes to build a material with which they can reinforce aging infrastructure and prevent people needing new, well, all the cost of demolishing things and new cement. And then Powwow Energy, these guys, what they really come down to is realizing that energy is water, water is energy. And they have a nice IT play of finding leaks and really helping farmers, agriculturalists well. And the Sustainability Award winner, oh, this was beautiful, Indoor Hydroponic Farms. And if I am correct in my memory here, in an indoor farm, you'd have a light source, you'd have something growing. Okay, great. In their case, they decided to make it cylindrical. So the light source runs down the middle. Think of it like a filament, and they're rotating their crop around it, so they just get much more yield per space. So what I want to leave you with is people are innovating like mad, trying to help the climate situation. And there's more. You know, there were 120 exhibitors, which included semi-finalists like us, Ice911, and alumni in many different categories. I forget if it was 6 or 8 different categories, all working hard on ways to try to improve the dreadful situation I just showed you. And of course, I always keep in mind, I showed you this at the beginning of the quarter too, simple can be best, right? This is as simple as bringing light to basically steel structures, well, metal structures, you know, by poking a hole in the roof and putting a bottle filled with water and a little bit of bleach into it and sealing it upright. And suddenly, when it's daytime outside, you've got light inside your home rather than a windowless place where you don't really want to be indoors much. Simple solutions. So moving on from entrepreneurship is alive and well and thriving in this space, let's talk about mitigation, adaptation, and geoengineering. So mitigation is everything about the Cleantech Open that we've just looked at and so much more. Conservation, energy efficiency, renewables, most of what we've seen the lecturers talk about this quarter in our class. And this is all needed, but it may be too slow to prevent major harms. It takes a long time to rebuild an infrastructure. If you have a better solar technology, it takes a while to get it installed, built and installed. In the meantime, sea levels are rising. We have, you know, difficulties in coastal cities for sure, and cities plan around it. And if you fast forward, at least where I decided to look at is, are there any Band-Aid measures that could buy us some time while we're doing all the things that we should do here in mitigation and adaptation? Possible emergency backup if all else fails. Remember that moral hazard, which a lot of you in your questions worried about. Well, if it's that simple, why don't we just keep on spewing out, you know, as much pollution as we want because some magic fix is going to take care of it? Isn't that pretty irresponsible? Yes. And it's actually why I kept my own project pretty darn quiet for a long time. I was like, well, I'm not sure I want anybody to know about it until we really need it, because you don't want it to be used as an excuse, but you might really need it. And so doing our homework up front is what people are doing. And it involves such complex issues. You really have to be careful. You sure don't want the unintended consequences, as Terry Root was really eloquent about, you know, just introducing one species in an area to take care of another one. Endless other consequences that you haven't thought about. And that always is an issue in anything you do, especially if you're thinking about doing it on a massive global scale. Could it be irreversible? That's a worry. And are the climate models good enough to figure out what you're doing? Who decides if you can do it? Who decides that they want it in their own backyard, right? These are all complex issues. Here's a Ken Caldera slide saying, okay, if I were to stabilize climate, here are some ways I want to do things. We could control long wave radiation by diminishing the energy demand, producing clean energy, remove things like CO2. Or we could control shortwave radiation, i.e. we could reduce the amount of solar radiation absorbed. That's one way to look at what we're doing. And here's another way to look at the Earth's energy balance. And it's, you know, it's interesting. You've got the incoming solar radiation, you're reflected by clouds, you're reflected by surface, you've got this whole water evaporation cycle going on, and then you've got the long wave radiation happening, where the greenhouse gases are at play here. So it's complicated. So the two distinct geoengineering strategies then, this is from the Royal Society Geoengineering report, because people worldwide are worrying about stuff like this, right? You can find things published. Carbon dioxide removal techniques, okay. There's some problems, it seems, with most of them. Again, Professor Brent Constance's one looks like maybe a way that some of this can be taken care of. Or there's solar radiation management techniques. And that can have a very quick response, but it doesn't get at the root problem. There are articles published that have all kinds of pretty pictures about many different ways people can think about doing geoengineering. And one that has gotten a lot of attention is this one of adding particulates, stratospheric sulfate aerosol injection like volcanoes, with the observation that after a volcanic eruption, temperatures seem to be reduced. So this again is Ken Caldera's slides. And in his case, and a lot of people tend to conflate geoengineering with stratospheric sulfate aerosol injection. It's the one that they're talking about when they say geoengineering. And people, I've been in a meeting about a year and a half ago where two different airplane companies, manufacturers, were coming in to say how they could get this to the stratosphere cheaply, you know, less than $1 billion. Oh boy. Personally, this worries me because I'm not sure our models are good enough to understand what happens with this. But I do understand the claim that one must do one's homework first to figure this out. And people are concluding, some of them, that this reflection of sunlight could offset some climate change a lot of the time. So again, this is Ken Caldera, and when he's saying turning on geoengineering, he's talking about stratospheric sulfate aerosol injection. It looks like a bailout, you know. If you turn it on, you can lower your temperature pretty quickly, depending when you're doing it. Great! What's wrong with this? Well, one thing is that if you stop, your temperatures tend to pop back up, perhaps to a lower curve now that they're going to asymptotically approach, but they're going to pop up quicker than they were rising in the first place. And that means enormous pressure on species again, and enormous, really quick climate changes. They also are, and so this means that your species extinctions and such may be worse off by starting something like this and then stopping it, which is a problem. Meaning you start, you may be committed for the long haul. The other thing that people talk about on this is that they're beginning to conclude now from the models that this will increase the severity of mid-latitude storms. That is, all these horrific typhoons and such. We may get more of them if we do it. It changes rainfall patterns quite a lot. So it's got risks, and it's got risks on the whole Earth. But you can understand why people are looking at it. I took a different approach. And coming as an engineer into climate, back there, you know, when I started this in 2006, I was looking for climate people to give me some feedback of, did this make any sense at all? And I keep being told that it does. Armand Cohen is the executive director of an outfit called the Clean Air Task Force back in Boston. And he's been very kind about this. I mean, this is his considered opinion. You can get the full quote on our website. But no question in his mind that this is one of the half dozen or so most important research projects underway globally on mitigating climate change. You know, that kind of feedback keeps you going. Why am I looking at ice? And notice, of course, Satish, who was here lecturing, we've known each other for a long time on this. And Shalini Venkatesh is a person I've been working with for years in small tech consulting, and new back at HP Labs. So one gathers terrific people along the way if you're really lucky. Why am I looking at ice melt? Why is it Ice911? And it's one of the problems is that the melt has accelerated far faster than those 2007 IPCC predictions. These were the predictions, IPCC, this was the whole range from that fourth assessment report. And what actually happened in 2007 and then 2012 were these spectacularly large ice melts. Everybody knew it was a positive feedback loop and it, you know, this was going to be accelerating, but nobody knew it was going to go that fast. And Chasing Ice, if you haven't seen it, I think it's out now that you can get a DVD on it. I've seen it twice with really great expert panels discussing it afterwards, right after it came out. Phenomenal film about how quickly the ice is disappearing in the world. So to go back to the video that we were showing, I'll show you just 3 shots from that. We're looking down on the Arctic. Same month each time, June 1980. This is from Age of Sea Ice by Rigger and Wallace, so that's where you can look it up, who was asking. June 1980, lots of bright reflective ice, some open ocean, some thin, you know, first-year ice, a little bit of second-year ice, you know, not very reflective, very reflective. Now, 20 years later, not much multi-year ice left. Last year, not much at all. Where you can see little artifacts here is where I was trying to block out all the satellite buoy, you know, diamonds and such. I was told this was a little confusing, but it really is darker here. There isn't much there. What does that mean? What are the effects? One of the effects that we're having more severe storms from the temperature changes and the rainfall distribution changes that are coming from the ice melt. And the horrible typhoon that we recently had with real human cost You know, people talk about numbers, but there are human beings there who, wow, what a situation. There are, of course, great opportunities for graphic artists. You know, this is from, I believe this is a photo composite of the Times Square, New York City subway system with a scuba diver in there, but, you know, not as far from reality as you might think. And there are these estimates. Many really credible outfits are now running estimate scenarios of what is it going to cost to shore up infrastructure against sea level rise and severe storms over time. And I've been advised from the Cleantech Open to only show a few data points at a time. So New York City, okay, $2 billion per year now to shore up their infrastructure. China, Guangzhou, 13 billion per year to shore it up. I mean, it's a worldwide problem. Many of these in Europe as well. And these are just some estimates. You know, at San Francisco, Bay Area, certainly we've got our issues too, right? And it isn't just, you know, some other places than ours. So many of us live in states where we've got a saltwater coastline. We're in a coastal county. I mean, it's a big deal. And the predictions are that after we get to 2050, sea levels will have risen enough. We're not talking billions a year anymore, but we're talking trillions. So, of course, we've talked about now mitigation. We've talked about adaptation right here. And we've talked a little bit about geoengineering. Of course, there's doing nothing, but this doesn't seem really good. When I say methane, I mean the methane releases from permafrost melt, from the Arctic Ocean melt. It's not a good scenario. So to summarize again, these options, mitigation, it is the long-term solution. It looks too slow. Adaptation, really expensive. Geoengineering, some of them look interesting. You know, I kind of like this saltwater mist one that is helping to nucleate new clouds to try to reflect more sunlight at that level because it's reversible, right? You stop it and things should settle down again. Some seem really risky. How do you get back trillions of orbiting lenses that you launch up? And what's the CO2 cost to do it? The engineering the atmosphere bothers me. But, you know, our backs may be driven to the wall. I took a different approach. What I decided to do was look into, as I call it, rebuilding the Earth's refrigerator by using artificial reflective ice. Been working on this since 2006, and we can address many areas, coastal areas, glaciers, snow, permafrost. Some of you are concerned, rightly so, about how on earth are you going to deploy at scale? How on earth will this not be causing additional problems? We'll talk about that, but those are some of the right questions. What are we looking at then? Back to that energy balance. We're looking at modifying the surface reflection here, and we're looking at not suppressing evaporation, which I think is really important. People, you know, what years ago were thinking about, why don't we cover the Arctic in a plastic sheet? Well, for one thing, you'd be rebuilding your pool cover. Because if you're suppressing evaporation, suppressing evaporative cooling, you actually warm things up. And I've done many tests in little tanks sitting here in this area in the sunlight, sunny afternoons, to find that you can have something like 13 degrees Fahrenheit, small tank. You can have 13 degrees higher under a white plastic sheet than in open water. It's really effective. But it's not going to make things cooler. So you want to be able to allow some evaporative cooling to go on. I'm pretty sure about that. And you want to not mess up, you know, getting your back radiation back out. My contention is, one of the ground rules on trying to engineer climate at all is that you want something that's going to be localized enough that you could, if you found, you know, let's call this uncontrolled temperature rise or uncontrolled CO2 rise. Let's say that we put something out there and it was phenomenally effective. In fact, it was so effective we drove ourselves to the next ice age. Not such a good outcome. So my contention is that whatever we put out there, we'd better be able to undo. And we have to make sure that we're not going to crunch. you know, you think, the Arctic, what's going on up there? It's cold, nothing's alive. Oh no, it's one of the bases of the world's food chain. So you really have to make sure. Somebody else was asking, I mean, I loved your questions. Somebody else was asking, well, gee, what's going to happen to all your sea organisms if you go and carpet something with some material? It's the right question. You have to make sure, I believe, to keep things as close to the natural process as possible. My whole thought is bootstrap the natural process. You could stop anytime you want. You won't bounce back. It's, you know, as in stopping the stratospheric sulfate aerosol injections, just keep it gentle. And so I've had, because this has been run on 7 years of volunteer work, I've also had the luxury, if you will, since it's not the day job and I don't have an academic reputation riding on it, you know, it's not, I don't have some boss telling me, you've got to do it this way, to just sit there and make the ground rules for myself. There's a joy in lack of funding in that way, if you will. And the ground rules I've come up with, I think are good ones. Fast to implement, sustainable, that is, don't be belting out more CO2 making this stuff than you're going to be compensating for. Ecologically respectful, boy, that's been number one in this 7-year search for materials. Reversible, well, I'm not sure that we're going to be able to pull this back. If we manage to freeze this into ice, I'm not sure we can pull it back out. But we can make it biodegradable, or we can say, hey, we're awfully good at soot. We could always scatter some soot around where needed. And you got to make it safe. And you've got these pieces of these 2 glasses sitting out here. This is regular ice right here. And this is our special stuff where we've made it brighter. You can see it's brighter. And because it's that safe. Don't worry, you won't have to follow me to the hospital later. It truly is that safe. I've done this before. And I think that's vital. We're very excited that we finally found the right material where you can do that. So what have we been doing? Well, we've been working hard. Of these 7 years, the first one really was thinking and figuring out what needed to be done. And then 6 years of lab and field tests have been really critical to development. There's Satish again. You'll recognize him as one of your speakers. Yep, you can if you want. Drink it if you dare. Here is Tony, whose pond we've been working on this year. We are so happy with that. And here's his friend Doug, who helped make our connection again. There I am with, pardon me, my cow hat. We worked before in the Sierra Nevada mountains for several years up on people's drinking water. This was nice. The Sierra Lakes County Water District was permitting us to work there because we told them exactly what our materials were. And those were things like the hollow glass spheres that I was very in favor of for quite a while, which are basically floating sand. But the problem is you're going to be working on somebody's drinking water. You've got to fence all this in so you can get it off later. No adverse effects in the water, but you really just don't want to clog up any filters or anything. So we worked for years on that. And now we're in this test pond laboratory in Minnesota. This is Tony's pond, so the person from 2 pictures ago, where he dug this pond when he built his house 15 years ago. And he's a retired PhD chemist, recently retired, and he is delighted. It's so wonderful to go out there and work on this and help us with our experiments. And he's just awesome. What that guy knows, it's wonderful. And so we got to test unfenced materials to catch the melt last March and April. And Satish came up. Now this is probably the 3rd iteration of our buoy and sensor platform. This is all Satish's work. And it's really pretty neat. And we've just put that out here. We were out there 2-3 weeks ago to put in the latest set of instrumentation and materials to catch the freeze. So this is worth the plane trip to have collaborators like that. And yes, after TSA showed Satish the love as he was trying to get this on the plane, there were a couple days of reassembling the buoy. But there we are. And this is Tony's basement. And it's really a pretty great way to work and do this. And we got to build these giant plastic cubes. We found the pond is small enough that if you have different test areas, they kind of communicate with each other if you're trying to test materials nearby each other. So this is trying to cut down some cross flow. It won't be perfect thermal isolation, but this surrounding the buoy now out in the middle of the pond, we got it in just before the freeze, allows us to put different materials in here and start testing them. And so for the March, April, so we don't have results from this last deployment that was just a couple weeks ago yet, but in March, April, when we were catching the melt, we found that floating glass spheres, so basically hollow sand, lots of people make very tiny hollow glass spheres, very bright, and they use them in paints and thinners. They're really good for a number of things. And we found that they were, using our little albedometers, handheld solar radiation meters, brighter than the surrounding ice, so we could slow down the melt, and we could see that. We used sheets. I used sheets a lot about 3 winters ago. It's miserable. Sheets equals sails. You have any wind at all, you have problems. You're just up there continually trying to re-anchor them. That lake up in the Sierras, we were doing that a lot. But they're so effective. And this happens to be a sheet of, it's a porous sheet. It's not just plastic, it's a very porous one. Has a high content of silica, actually, like the floating glass did. Nice and effective, but even a teeny sheet like this, we're chasing it around this pond, mostly Tony, chasing it around. Biodegradable materials, very nice. In fact, I think biodegradable materials, or something safe enough to drink, is really a really promising way to go. And that instrumentation, I'm just happy with what Satish has come up with. He's got a plan now to make something even lighter and smaller. The ice additives, we just had this breakthrough a couple months ago, and I could hardly contain myself. I finally went and tried the simplest possible option. I will not say it out here. Sorry, I don't want this out on YouTube, but it's the simplest, safest thing. And and why don't I want it out on YouTube? You'll see in a couple minutes. Certainly anybody whose pond we're experimenting on needs to know, and we'll give them full disclosure. Certainly we're being very above board on this, but we also think that we could maybe start up finally some profitable businesses from something like this, and that might give us the funding we need to help this work get out to the Arctic. So while we filed some initial IP, we also need to publish our paper on this. We're just not saying this too loudly yet, what it is, but it's really safe. And it was such a simple thing, finally, after 7 years of looking at various materials to find something this simple. But it's profound. It freezes faster, it lasts longer in the sun. And remember, the ice experts tell me, Don Perovich in particular, Dr. Don Perovich in New Hampshire, that if you can extend the melting season just a couple weeks, or if you can start it a couple weeks sooner, at either end of the summer here, extend a little farther into the summer or start it a little sooner into the fall, winter, you can make a profound difference in how quickly that ice disappearance is happening. And you can maybe fend off, at this point, the estimates are 35% of temperature rises from this loss of the Earth's refrigerator up in the Arctic. So you could really slow down some of these effects a lot. And I must say the world is getting kind to experimenters on a low budget now. You can get immersible temperature sensors for not much now. And so I've put them in these buckets that you see in the photo there. It's these nice little immersible temperature sensors, and let them go through the ride in a freezer. You can let them freeze up like this, and then you can let them melt. So regular ice and this safe additive, just like what's in the glasses that you have there. And you can watch the slower melt. We should be back on the chart, please. Thanks. You can watch the slower melt with the additive versus with just plain old ice. So it's freezing faster, it's lasting longer. This is really, really interesting. And this is by far the lowest cost material that I've been looking at yet. This is actually 1 to 2 orders of magnitude lower than the cost of anything else I've been looking at, including, my old favorite, the hollow glass spheres. Why 50,000 square kilometers? That was the historic summer-to-summer ice melt in the 90s. And so this is a very thin layer of bright ice that I'm costing, but it's comparable to what I was thinking with the hollow glass spheres. 35 million. that becomes doable, right? I mean, any sizable philanthropist could do that. Now, that, of course, is just the material cost for the additive. That isn't making or transporting the ice there and getting it deployed. Granted that, but at least the material cost is low. We're lucky that we've got a world-class team. You know me now. You've certainly heard Satish talk. Shalini is really great. And we've had this governing board and advisors. If you've checked out the Ice911 website, maybe you've seen some of these names, including Terry Root, one of the Nobel Prize co-recipients. Just phenomenal people. And then through the Cleantech Open, we got a whole new set of mentors helping us. Kimberly is now helping us. You remember Kimberly's great workshop. She's now helping us a lot. David Rumler was auditing the class for a while. You might have noticed him coming in. Really nice. We're still pending on our 501c3, but we're at least getting responses now that are telling us the process is moving along. We were approved in California quite a while ago. Now we're just waiting for the federal approval. But how the heck do you fund something like this? This has been one of the ongoing dilemmas. I'll say that at this point, we've gotten this far on a little under $200,000 of donations, primarily from my neighbors, my friends and neighbors, who know that I do what I say I'll do. I volunteered in the schools a lot when my kids were, well, they're still in them, over the years. And people who know me that way have said, okay, I hear what she's doing. I like what she's doing. I know she'll do what she says. I'll donate. But my goodness, grants have been tricky because geoengineering, this falls under that label, though Steve Schneider, the late Steve Schneider labeled it eco-engineering. I've been to a workshop on soft geoengineering. There's all kinds of labels but it still gets lumped in with geoengineering. And some of those options scare some people, right? Some of those options scare me. And so that's made grants slow to get, but things I think are changing as the situation gets worse. When I started this was the option I hoped we'd never need. It was the backup option of, let's hope we'll never need it, but it's looking more and more important. And I think the world is changing so that the grants may be able to come. We're going to try crowdfunding, and I think we're going to try crowdsourcing a game. I think I'm tired of sitting here. And our game is going to be Dice 911. You're playing dice with the climate. With little stickers, the Ice911 logo sitting on the 6 side and going there. And I think that will be our giveaway for our crowdfunding. You can go through, and people are funding climate projects this way. I just read about some individual lakes in Ontario that have been used for looking at acidification, water acidification, that were kept alive through some crowdfunding efforts. Really interesting. Accelerators like the Cleantech Open, that's not the only one, but it's a great one. Sponsorships and partnerships with industry, with academia, and then profitable subsidiaries are the ways that we know to look at funding and deployment. And we're going after it because we've got the right material now and the situation's getting worse. And so all of this is trying to generate the dollars so we can do the R&D to be able to deploy at scale in the Arctic. Are we trying to cover the whole Arctic? Heavens no. If we can pick critical areas on glacial melt ponds around the coast of Greenland, maybe in Hudson Bay, maybe off the coast of Alaska, critical areas, and start there, that's the way to do it. You don't want to try to have to carpet the entire Arctic. Donors, we've had, these were 28, I think, different families who supported the work over time. And that's how we've gotten this. No salaries, but the instrumentation and travel. But here's the development plan, developed with the aid of what we've learned at the Cleantech Open. All these public uses we've been looking at, glacial melt ponds, permafrost, snow, sea ice, but then commercial uses too. Because when you know how to cool things, you know the world needs cooling too. So we're looking into that. And that's why I'm being quiet about specifically what this marvelous whiter ice is about. What do we need from here? About 2.5 million, we're thinking, over the next couple years to really get this out there. Deploy in Greenland. Somebody asked, what are we trying to deploy? We're trying to look at a glacial melt pond, and we're timing it. Why April? Why April 23rd to 26th? Doug Staup who was here at the beginning of the quarter lecturing on his Arctic and Antarctic explorations, is running a ski tour and an ultramarathon in Greenland at that point, and he is so tied in with the community there, because this is not his first time there, that he's going to, they've agreed from his asking to help us make some deployments there. It's a nice way to get in there. So this is one of the slides I showed at the Cleantech Open as I was finishing off a talk, and again, more graphic artist fun, but the concerns are real, right? Here's a disappearing New York City as sea level rises. It's very costly, though. Graphic art fun or not, it's very costly. We've got a solution here. It looks like we could even make some profitable, sustainable companies, which is probably the right way to get it to scale. And we're working now, Minnesota, California, heading to Greenland, should we get the funding. And that's the end of the Ice911 story for now. But it's an exciting one, and if you're interested in staying informed, send me an email, and I will put you on our distribution list for updates and things.